I think we are ready to start. A couple of words of introductions for Professor Ichul Yoon, who is associate professor at the University of Kansas. And normally I would highly prize him for his research. Again, he's one of the leading experts on figuring out these microarchitectural attacks, as well as really sources of contention that really hinders our understanding of how platform under stress behaves in terms of temporal performance of our application. And I started investigating this as, okay, let's spot problems and figure out how to solve. And these things evolve into actually the problems that we have in our architecture these days are so big that you can mount entire attacks against other programs on the same machine, right? And today is gonna talk about this research in that domain. But again, normally I would stop there, but I also want to spend a couple of words to say that Ichul is not just an amazing researcher, he's also a dear friend of mine, and we go back to the UIUC years when we were PhD students in the same, well, in sort of a twin labs between my advisor and Professor Louis Shah. So we have some common roots there. But other than that, I just want to wrap up this so that I can give the stage to Ichul. Please welcome Ichul.
Introduction, and yeah, I'm Ichul Yoon, and well, I'm going to talk about the microarchitectural denial resource attack and defenses of a physical system. So, as we know, that modern physical systems like drones and the self-driving cars are essentially a combination of the powerful computers and physical system. And many of these systems are real-time systems because they have to interact with the surrounding environment in real time. And also they are safety critical because they can cause real harm. And increasingly they are connected. So all those cars that get software from the internet, and they are increasingly intelligent, right? So all of these means that we need powerful computer, and these highly integrated high-performance system processors are widely used in this kind of system that may integrate multiple cores, GPUs, accelerators, and so forth. So this is great because they can provide high performance and efficiency, but also they created new challenges in terms of safety and security. So microarchitectural attacks are one of those challenges. So they means basically software attack that target hardware, microarchitectural components. And probably many of you guys already know about is Meltdown, Inspector, MDS, and so forth. These attacks are basically microarchitectural attack that can leak secret. And also another kinds of the microarchitectural attack would be row hammer attack, which also you may be heard about it, which can alter the data stored in memory, right? But what I'm going to talk about today is those that specifically influence execution time inside a physical system, because inside a physical system, the time matters. So it's not just the producing correct value, correct answer matter, but also when the data, when the answer was produced, matter in terms of the correctness and safety of those type of system. So because of that, we can conceive this attack that are specifically designed to increase the execution time of the victim. So here, what we are assuming is that the victims and attackers are co-located in a single system. So the attacker's goal is to increase the execution time of the victim. And so, of course, we want to, we assume we deploy some basic countermeasure like the co-partitioning and cache partitioning. And these are the kind of standard way to potentially mitigate this type of attack. But the problem is we might not be able to do so. Let me explain. So first of all, so why this kind of attack matter inside a physical system? For example, this is a little demo that we created to illustrate the potential. So here, the the car, if I can play the video. All right. So the car is controlled by a neural network-based agent that drive the car, steer the car based on the input video processing video. But as you can see, when we introduce the attacker on some of the cores, the car controller meets the deadline because the interference caused by the attacker affect the execution time of the controller, and eventually it crash. So obviously this is kind of a simplistic kind of system for example, but you can easily see this could be a problem in more complicated autonomous system. Do you have a question?
Yeah, I have a question.
Okay, sure.
You said that you assume that the attacker has the caches of partition. Does that include the last level cache?
Yes.
So the last level cache is partitioned somehow by.
Yeah, so we can, so basically the basic assumption, of course you can apply different assumption, but we assume the cache is partitioned, and maybe even we can deploy more stronger kind of defense against those attacks. But let me explain those attacks and what we are thinking about in terms of the attack feasibilities later. So over the years, basically we have discovered many hardware interference channel that can be used as a potential DOS attack vector. So in the rest of the talk, I will first talk about those channels and to understand why this channel exists and how significant this interference channel could be. And then I'm going to talk about the case study, which was proposed by ARM as a part of the industrial challenge. And so this challenge is kind of, illustrating the potential problem of this interference channel. And finally, I'm going to talk about hardware level defense that can mitigate these kind of problems and also their limitation. So let me start with the interference channel. So the most important thing, I think, to understand the modern multi-core architecture is this memory level parallelism. So what that means is basically we want to allow multiple concurrent memory requests to be processed. And this is important for performance because, as you know, the memory latency is huge compared to compute. And so these modern architectures are designed to maximize the parallelism in memory accesses so as to kind of mitigate those memory latency issue. And so the cores can generate many tens of requests simultaneously, so does the bus. And the cache and memory are designed to maximize these parallel accesses. And this is a basic common characteristic. If you look at any of these high-performance SoC, you will see the design, the hardware aspects that are designed to maximize these memory level parallelism. So if you look at these cores, out-of-order core can generate many tens of requests. The caches are not blocking, and memory controller may be buffering multiple requests and may even reordering. And DRAM and caches are organized in ways that allow you to access concurrent requests. So one of the important shared resources is, of course, the bus interconnect. But contrary to common belief, the interconnect is actually not usually not a major bottleneck because it allows concurrent requests and also they offer generally high throughput. So then what is the problem? The problem usually lies in the edges. So the caches and main memories and memory controllers. So let me talk about the cache first. So the caches in modern computer systems are non-blocking. What that means is that you can allow accessing caches while the cache is processing multiple outstanding misses. So for example, if you look at this figure, so instead of blocking every time you have a cache miss. The cache can continue to operate as long as you can find instruction that can, you know, you can independently execute. So the non-blocking caches are basically essential for not just multi-core, but even the single core in these systems. So in order to enable non-blocking caches, there are hardware structures in those caches, such as misstate transporting registers and write-back buffer, that allow you to have this non-blocking behavior. So these internal structures are hidden to users, of course, but they are essential. They are commonly existing in modern non-blocking caches, and they can be potential interference channel. I will show you the impact of those interference channel later, but another main common aspects of the modern memory system is that the cache and DRAMs are organized in ways to have multiple banks. So we often think the cache or DRAM as a single resource, but it is actually not a single resource. In fact, it is organized of the multiple resources called bank, and these banks allow you to access in parallel. And so in general, if you have more bank, you have more parallelism and higher throughput, which is great. Yes.
I'm sorry, I'm still a little confused. I thought that you said the caches was segregated between attacker and defender, right? But here you're talking about the caches being shared.
So the cache is shared cache, last level shared cache, but we can apply partitioning technique to provide space
so the
partitioning,
shared
right?
cache
Yeah.
with partitioning.
Right.
Okay, so something is shared, otherwise I don't know.
Yes, exactly.
You don't get that side channel.
Yeah.
But what's interesting is that the space partition doesn't mean that you're necessarily dividing the banks.
Of course, right, yeah.
Yeah, so that's basically, yeah, I think I should have clarified that, yes. So we assume the shared cache that is used by both attackers and the victim. And then the cache may be partitioned, but space partitioned, but not other things, right?
Okay, that makes more sense.
Yeah.
Otherwise, I thought you were totally magic rabbit.
Yeah, of course, yes. I'm not a magician, of course. So, so the bank organization is kind of very important to understand this, modern architecture. So, for example, if you look at the cache organization of this Cortex A72, so this is the last level cache, which has, two tag bank, and then each tag bank is composed of the multiple data bank. So basically, these tag banks can be accessed completely in parallel. So if you, access these two, if you access your memory, and then, depending on the physical address of your memory access, it could be tag bank 1 or tag bank 2, and then if you access these, these two banks can be completely independent. So likewise, the DRAM is also organized multiple bank. So for example, in case of the Raspberry Pi 4, which has 16 bank, what that means is basically depending on your physical address, you may be accessing one of the 16 different bank when you access the memory. So of course, the bank organization is to make parallel access more efficient and possible. So the problem is that this multi-bank organization is great when the accesses are evenly distributed. However, if the accesses are not evenly distributed, then it could be a problem. So for example, in the worst case, all these cores may be accessing a subset of bank, given just one bank. Well, then the problem is that this bank, the single bank that is being accessed can be severely contended, and that could cause significant delay. And the same is the case for the cache. So if your memory addresses are such that you access a single cache bank, then that cache bank could be contended. So now let me explain. Oh, before I go to the evaluation result, I want to talk about briefly talk about the memory controller issue. So of course, in modern system, the memory controller does have buffer and scheduler, which also can significantly affect the execution time the victim may experience, because they may reorder the request in such a way that, depending on the access pattern, the request from the critical application may be significantly delayed. So now, based on this understanding of common characteristics of the modern architecture, we can come up with the effective strategies that can cause severe interference. So in general, these are very simple. So one effective strategy is to try to exhaust various hardware resources, the buffers and the queues. And another is to try to generate many concurrent requests targeting a single resource rather than distributing those requests to multiple resources. Finally, we find that the write request often cause more severe interference than read for a variety of reasons, including the scheduling algorithm employed in this scheduler in memory controller and others. So let me show you some of the experimental results that we have obtained with deploying these techniques. So this figure shows the cache attack that specifically targeted to exhaust the internal buffers in the shared cache. So here, the attack is very simple, just sequential access, sequential write specifically. And what you see here is that the victim that is running on one core is experiencing up to 300x slowdown, even though we apply cache space partitioning so that the attacker cannot evict the cache line of the victim, and the victim is accessing its own private cache partition. So the victim is having 100% cache hit, yet it is experiencing up to 300x slowdown, more than 300x slowdown. So obviously, this is kind of very counterintuitive. Initially, we were surprised by this result because we thought that, well, we partition the cache space. So as long as I'm having cache hit, my working set size fit into the cache partition, we shouldn't see slowdown. It turns out not the case. Why? Because of those shared resources inside the cache, the internal structure can be exhausted, and in this case, indeed, they are exhausted. And when they are exhausted, the entire cache is blocked until those hardware resources become available again, and they may take 100 cycles. And because of that, you may see this kind of crazy slowdown, which is completely unexpected.
Here, your mem bombs are creating a lot of write traffic, right? So a lot of write allocate write backs.
So in this particular case, we believe this is due to the write back buffer exhaustion, but also MSSR could be the source of the contention. So another experiment that we did. So in this case, the attack is specifically focusing on DRAM bank. So here, yes.
Sorry, what are the specific specifications? They're using what specific DRAM or what specific?
So this is, we have tested on several embedded platform. In this particular, in this case, it is, the Odroid XG4 platform, which is LPDDR for, I think LPDDR. Yeah.
I'm just surprised that they have no load balancing, nothing.
Mm-hmm.
They don't have any load balancing. I mean, this is a well-known.
Load balancing.
It's more of a head of line blocking, because at some point when you exhaust all of them,
Yeah.
the next one, while you're waiting for the first one to come back because of the memory latency, the next one, even if it's a hit, gotta wait.
Right, but you shouldn't allow all the writes to occur from one partition, right? You should do some sort of load balancing.
Between the cores,
Yeah.
in theory, yeah, oh, yeah.
That's
The
not
perfect
this.
word.
So, sorry.
You shouldn't allow one particular core to exhaust the entire
Oh,
shared resource.
yeah, you might
There should
think
be some
so,
load
right? So
balancing.
basically architecture should be designed to prevent such a kind of
Yeah,
situation, right?
yeah.
But it wasn't, and many of the platforms that we have tested didn't have that kind of. I mean,
Is this specifically
so
for
I'm
IoT?
actually going to talk about a little bit of a hardware aspect as well later.
Okay.
But basically, this is experimental study that we have conducted. Experimental study on a number of different hardware platforms, and especially focusing on embedded platform. But all of these platforms that we have tested, we found that we were able to exhaust those resources.
So, as a follow-up question to that, does that mean that a scheduler is needed in the hardware to do the load balancing? A
Excuse me?
scheduler, is a scheduler needed to do the load balancing in the hardware?
So we are going to talk about what are the things that hardware need to do better later. But basically, right now, many platforms that we rely on, for example, Raspberry Pi that you probably use, right? They don't have any way to prevent this kind of situation from happening. So when there are finite buffer hardware structure, right? They're usually finite, and then they are designed. I mean, it's determined at the design time, and then they usually budgeted according to the average case, right? So the worst case situation like this are typically not considered, and when they happen, this kind of very severe contention can arise, and we have observed this behavior over and over many different platforms in real products that we have tested. Okay.
Remember, ARM, right, just gives blueprints and kind of like reference designs, and a lot of manufacturers use those. So a lot of this problem exists because they all come from a common root cause, right? But even on Intel platforms, this kind of not built in. I mean, there are other mechanisms like hashing in Intel platform that will make things harder, I think, to exploit, but still fundamentally.
Actually, the Intel is not much different in the sense that it's just more obscure, and it's kind of more difficult to access. But once you get the information that you need to, then you can exploit the behavior. Yes.
So I'm a little surprised that the write back all the queues that you have are not partitioned physically with the space itself.
Mm-hmm.
So they're just or per section of cache that you're separating out.
But there's one thing that you have to remember, right? In a write-back cache, there is no such thing as core ownership for cache lines that are written back, right? Because the write-back is not triggered by the core that has dirtied the cache. It's just triggered by the eviction, right?
Yeah.
So really, that is why there's no sort of per core queues. It's just.
Well, I'm not suggesting do it per core, but you should be able to assign queues to go with the partitioned cache space.
Oh.
So cache partitioning here. I mean, so to clarify, this is software-based cache partitioning, specifically page coloring-based cache partitioning. In this particular example, but the way partitioning doesn't solve the problem in the sense that yes, I mean anyway. So this is the main important point is that there are structures in those caches and others that are shared, but we don't see usually. And when you have shared hardware structure, you can easily exhaust those structures in such a way that can affect everybody that access the entire resource, in this case cache, right? So that's the main takeaway of this experiment. Now, so that is basically how we can create significant delay by focusing on internal hardware structures. So now I'm going to talk about how we can exploit this multi-bank organization in the DRAM and in the cache. So let's start with the DRAM. So of course the DRAM has many banks. If you know about the DRAM, then DRAM is composed of multiple banks. They can be accessed largely independently in parallel, not exactly independent, but they are basically assuming on average requests are distributed over all those banks, right? However, so here, what you see here is that you can actually create those concurrent requests specifically directed to a single DRAM bank. If you do that, then you can actually create much higher delay. For example, in this case, 40x delay, compared to the sequential access. Which sequential access is actually generating more bandwidth. So even if your bandwidth generation is much lower, if you direct your all request to single bank, the actual impact is much higher. So here, for example, this white line is basically the sequential write, the man bomb, if you will. But then they are, of course, generate huge delay, but not as great as this one that we engineer those requests to a single bank. And this actual bandwidth, if you measure the bandwidth of this attack, the actual consumed bandwidth is much lower. In fact, a fraction of the bandwidth, you can actually generate much higher delay, because if you can basically prevent the access to that bank, the application, the victim, may be waiting that request to be serviced in order to make progress, and therefore you get this high delay. Now, the same thing happened at the cache level. So when we design the attack, do you have a question?
Yeah, sorry, for the previous slide, you have the bank or parallel pointer chasing. Does that mean that you're jumping around, following pointers
So I'm
inside
going to
the same
talk
bank?
about exactly how we did that, but basically it is a multiple pointer chasing kind of application that you access multiple linked lists, and then they are essentially
In the same bank? Is that like?
So we chose this linked list entry in such a way that you can these addresses are mapped to the particular bank. Okay. All right. So again, the same thing. Yes.
Without operating system access.
Sorry.
Without operating
Yes.
system access. So you're doing this on top of
Right.
Linux.
Yeah.
How did you get the vert to physical mapping?
So mapping is, of course, require some reverse engineering, right? So in case of DRAM, so here, okay, so there are a variety of techniques that allow you to reverse engineer the mapping,
Sure.
the DRAM bank mapping, and so that's what we use. In the case of the particular platform, some platforms are easier to reverse engineer. For example, Raspberry Pi 4, they just use 4 physical bits. Then that's it, and you can actually very easily reverse engineer what bits will determine the bank accesses. So you can use that information to create the request to specifically target a certain bank.
I think
It doesn't change.
So yeah, it is hardware baked, So once you configure the memory controller has, it is fixed that you cannot change it. And actually that's the kind of the danger that I'm going to talk about now. The cache bank attack is even easier to mount, because the cache, the bits that control the cache bank accesses are usually very low in the physical address bit, so that you don't need any special privilege to control what cache bank you can access.
To Eric's question, if you were asking about how you control the bits, the physical bits in user space, I think they use huge TLB mapping.
So in case of in this paper, yes, it's DRAM bank or attacks. It also depends on what physical addresses are mapped to the bank mapping. So some platforms use kind of low, below the page map, then it's easier. But if it is kind of below 4K boundary, then it's kind of a little bit more difficult. You need some support in terms of the using huge page. But huge page is standard in many of the systems these days. So it actually gives you a lot of flexibility about what kind of address.
And it answered the second part of my question, which is going to be about: are you pinning pages? Are you preventing migration? Like, how are you dealing with when stuff moves around? But if you're using pages, you are pinning.
Yeah, you can pin by default.
Yeah,
And also,
exactly.
a lot of new kernels use auto huge pages anyway. So as long as you allocate a big
all you need is basically, physically contiguous big chunk of memory, then it gives you a whole bunch of possible attacks that utilize those mapping information. So the cache bank attack is the same concept that you just control what cache bank you access, and then we found that targeting the same cache bank can create up to 10x slowdown on. In this case, this is a Raspberry Pi 4 and just a Nano. As you can see, they use the same shared cache, and as a result, we can easily create this significant slowdown. And what is interesting here is that the other case, when you access different cache bank, then the same attacker that target different cache bank generate no interference. So you basically have zero interference if you target different tag bank, which means the interconnect is not the bottleneck, but the bank is the source of this interference. So this is basically using, so previous result is using synthetic task that we control everything, but here, even in real application, when you run this real application as a victim, you can easily mount an attack that by targeting the same. So here, what is interesting and important is that, again, the cache space is partitioned so that the victim and attacker cannot evict the cache line of the victim. And also, in this case, we employ DRAM bandwidth throttling, which is another popular mechanism to defend against this type of attack. And they both are ineffective. Why? Because this attack doesn't generate any DRAM traffic because they target, they fit into the cache space that is given to the attacker. And so all they do is simply generating a lot of cache hit. But they are targeted to a specific cache bank, and that enable more than 2x slowdown in real application that is accessing private cache space. So I hope this kind of quick overview of modern architecture that are designed to maximize memory level parallelism can potentially be a significant interference channel from real-time systems perspective. And contrary to popular belief, as I said, interconnect may not be the bottleneck, may not be the problem. So if you kind of try to prevent this type of attack by designing some interconnect level solution that might not be effective. So the major one that we found are on the edges, meaning the cache and DRAM and the memory controllers. And these attacks are very effective in creating massive cross-core interference, and they cannot be easily mitigated by existing mitigation methods such as cache partitioning and even memory bandwidth throttling. So now I'm going to talk about a case study which was proposed by as an industrial challenge problem. So the challenge is basically centered around this augmented reality heads-up display. This is an automotive application. As you can see in the picture, it's basically about creating this kind of augmented reality display that show the trajectory of the cars and like the obstacles and other type of information. So the challenge problem consists of a couple of applications, real-time tasks, which was defined by So the first is the SLAM, the visual SLAM. The visual SLAM is basically using the camera input, you determine the trajectory, so you localize yourself within, as well as you create a map of the surrounding environment. And ARM defined this task as high criticality real-time task. And another task defined by ARM is this task pose estimation. Basically, drivers pose will affect how this display should be projected on the screen. And so this is a neural network based one, and that is also denoted as high priority real-time task. Okay. And so here, what we are talking about is they assume aggressor task, which basically can be either benign or malicious. But the point here is that these tasks are non-real-time tasks, but may still compete the shared hardware resources in the system. So we took the challenge and we kind of first analyzed this impact of these microarchitectural attacks in this challenge application. And also we propose a solution that we can prevent this type of attack. So the particular platform that we chose to use in this study is this Jetson Nano, NVIDIA Jetson Nano. Here it is quad-core processor with integrated GPU. So we give a dedicated core to the two real-time tasks, the SLAM and the DNN. So the two core for SLAM, and then a core and the GPU is dedicated to the DNN task. Both are real-time tasks. And this particular platform has shared the cache, but the cache is not being shared with the GPU, but the GPU do share the DRAM with the CPU cores. So this is the basic platform. And so we assign the real-time priority to the real-time task, two real-time tasks, the SLAM and the DNN task. And then we basically, collocate the aggressor task, basically DOS attack task, as a best effort task, meaning that the scheduled with the default CFS scheduler to fully load the system. So from the CPU time perspective, because we use a real-time scheduler to schedule this real-time task, this aggressor task cannot affect the scheduling of the real-time task. However, they may be able to impact their execution time because whenever they are scheduled, they access same shared hardware resources, and that is the basic, the problem that we want to see how much of impact that might be. So now I'm going to show the exact code that constitute this attack. So we basically use these two very simple synthetic tasks as an attacker. So one is the sequential write, and another is the what we call parallel linked list attacker. But basically, these are multiple linked list pointer tracing, and it can generate many parallel requests. All of them are dependent from the previous entry, and so you can configure their working set size and memory access pattern, read or write, and then importantly, the cache bank aware attack is basically the parallel linked list attack, but when you create the linked list, we basically chose addresses, the physical addresses of those entries to be aligned to a specific tag bank. So with that, so here you can see the x-axis show the different types of the synthetic attacker task. And the y-axis shows the absolute trajectory error of the SLAM application. So the leftmost is when the SLAM is running alone, meaning that the trajectory error is very minimal. But depending on the aggressor task, the US attack task, you can see the varying degree of the impact in the quality of the SLAM trajectory generation. And the most effective one are those that target same cache bank. Okay, so this attack, the cache bank aware attack, is the one that we're gonna use in the rest of the figures. So here, what you can see here is that this is a kind of the projection of the trajectories generated by this SLAM task. And what you see here is that when it runs alone, of course, the SLAM is very accurate. It is very close to the ground truth. But even without the attacker, even without the DOS attacker, when you co-schedule the DNN task, which runs on the GPU, by the way, is having significant impact to the quality of the trajectory generated by the SLAM. And that is because this is not because of the cache bank contention, but because of the DRAM bandwidth contention, that the CPU and GPU share DRAM, and therefore, when you have this DNN task is running on the GPU, that affect the SLAM task running on the CPU. Now, when we add the cache bank attack as a best effort task on the background, the SLAM task completely failed to generate any valid trajectory. So it completely failed, and that means, of course, a big problem if this is a real system. So the solution that we propose is basically a combination of the throttling technique. So for the cache bank aware attack, we implemented a software-based cache bandwidth throttling technique, which built on our prior work on memguard, which used performance counter to monitor the bandwidth that is generated by the attacker and regulate the maximum bandwidth to a certain limit to minimize, to bound the impact of the contention. And then the GPU bandwidth throttling is basically, hardware supported capability in this particular platform does have a hardware-based, throttling capability that we can use for throttling the GPU. And then finally, this is a scheduling technique, which I'm not going to talk about details for this work, but basically, we use this combination, and the result is this. So what you see here is basically after we apply this technique that we proposed, the SLAM task is now, almost close to the Solr execution, meaning that it is creating a valid trajectory, even though we have, attacker, the DOS attacker, post-scheduled in the background of the system. Compare this with the Quorum, which is without our solution, it basically failed, as I already mentioned before.
So you have this mechanism to regulate the bandwidth, right? How do you actually tune it? So how do you set the set point?
So that's the kind of the main point. So here, in order to make this happen, we have to throttle the attacker so much, it basically almost not running at all. And that is, if you so we specifically set the bandwidth of the cache access to be 100 megabyte per second. For example, 100 megabyte per second for cache is very, very, very small, right? So of course, that's the cost in this case. The cost of the protecting the real-time task is very high.
Yep.
Why? Because this is software technique, and we don't have any ability to observe which bank these requests are going through.
Oh, okay. So that answers the question.
But would you be interested in methods that, for example, say, all right, we don't necessarily want to bring back to solid performance, but we accept a level of control degradation, and then whatever that means for the core rounding regulation level, that needs to be applied. But the goal is really slowing down the main trajectory following, but only so long as it doesn't slow down by more than 20%, something like that.
Yeah. So basically, you can come up with a solution to dynamically throttle just enough of the bandwidth so that you can have acceptable performance. So you can always balance it. But the problem here is that the balance is still very inefficient because you don't have a visibility of the bank level accesses. Yes.
But how, as if you don't have the visibility of the bank, how were you able to do that before that?
So basically, we have to assume worst case scenario. So basically, the worst case scenario is they're always going to target the same bank, and then based on that assumption, you have to set the budget to prevent the impact of the contention to be sufficiently small to protect your real-time task. And that is the one that I'm going to talk about next.
No, the attacker can use memory mapping to decide where to attack. The regulator has no clue where the accesses are. It just sees a counter of accesses to main memory, uses that to regulate. It has no visibility of where the accesses are.
Yeah,
Right.
but I mean, if the attacker has in software the ability to attack certain banks, can't I write software that will just assign a bank to a certain
Imagine
bank?
that you are a person coming to this room, right? You know where you want to come, but your regulator just counts the people that come through the door at the entrance of the whole building. That's what you can regulate.
So I think the point is that if you have a visibility, yes, you can take that into account, but you don't have a visibility because the hardware doesn't provide that, to you. So there's no way to see from the hardware performance counter which bank my request is going to, and that is a problem which I'm going to talk about next. Because so the problem here is that, as you have hopefully convinced, is that when we consolidate real-time and non-real-time tasks in a heterogeneous multiple platform, the interference can be a real problem that can affect the safety of the system. And in this particular case study, we find that the cache banker attack is especially effective because the SLAM task turns out to be very sensitive to cache performance, and that if you target a specific cache bank, you effectively reduce the performance of the cache significantly. So that's why we have this high degree of impact. And now that is, so basically we have a software solution. The problem is that this is based on software, and then it always have limited in the sense that we don't have any visibility of which bank these access are going to. And so we basically have to take the worst case scenario. And also it doesn't have that we rely on the interrupt handler and the timer interrupt handler to monitor and regulate. And this is also not ideal. So now I'm going to talk about the hardware level defenses that are already existing in Intel and ARM processor, and why they are not sufficient to fix this problem efficiently. And I'm going to talk about our solution, hardware-based solution that mitigate this, address this limitation to some degree. All right, so better hardware support is needed, and then you may ask, why not just use something like Intel RDT or MPEM? Also, those techniques are architectural level support to mitigate precisely this kind of problem. At least that's the intention. But what actually they do is basically providing cache weight partitioning and memory bandwidth throttling. So that is what they do, right? Both Intel RDT and MPEM, they have these two basic capability essential for them. But as the work that we have done with Minato have demonstrated, Intel RDT's capabilities are not sufficient. And then we believe the same is the case for MPEM, because again, they do only cache space partitioning and memory bandwidth throttling, which are not sufficient. So this is all the capability that MPEM is supposed to provide, but the gist of it is that it has this cache weight partitioning capability, so that you can basically determine the subset of ways you can allocate a subset of cache weights to a particular cores. But the problem is, well, this is about ways. It doesn't tell you about the bank. There is no way to control the bank. And as I already demonstrated, if you can control the bank, because the bank mapping is usually something that attacker can easily access. And then when you do, space partitioning provided by this weight partitioning capability doesn't help you to prevent the attacker's influence to your real-time application. Another problem, another capability, the bandwidth throttling, the hardware level bandwidth throttling capability is useful And when you do it at the hardware level, then you can remove the software level overhead, like the member does. But as I stated already, these techniques rely on the assumption that higher bandwidth will cause higher interference. That is not true. So the kinds of the bandwidth matter a great deal, specifically if you can engineer your request to target subset of bank that can be way more effective, even though the bandwidth consumed by these attack are much lower. So then when you have this kind of characteristic, it is very difficult to come up with the effective bandwidth throttling technique. And that's the problem that we believe is not currently considered in this type of hardware support. So this is a kind of wish list that we have. So we need a better monitoring throttling capability, specifically the bank-aware observability and throttling capability are needed. And then we need a better control over the mapping. The mapping in the sense that the physical address to the resources. Those mapping are baked in hardware currently, and you cannot change it. So for example, once the L2 cache design is fixed, then you cannot prevent this cache bank attack because it is there and then you cannot do anything about it. So we believe this needs to be changed in ways that allow you to control this mapping at the software level. And then we want to have a better control about the resources, internal resources, and also we need a better abstraction. By the way, this memory abstraction, again, we have some work together with Minato in the past, and basically we believe we need a more aggressive memory abstraction that allow us to express this kind of different requirement for specific application. So over the years, we kind of focused on actually doing something about it by designing hardware that address these problems. So we specifically focus on RISC-V based infrastructure. So we have created RISC-V based research platform that we have utilized. And so one of these, early work that we did is basically creating the bandwidth regulator ourselves, which is called BRU. So the BRU is having the hardware level bandwidth capability, much like Intel RDT or MPEM, but it does have this group level regulation capability that allow us more flexible bandwidth control. And however, this BRU doesn't have the visibility of the bank level visibility. So more recently, we have proposed the bank-aware bandwidth regulation technique, specifically to address this cache bank-aware US attack. So as I mentioned, the problem of this cache bank-aware attack is that we cannot, if you target a specific bank, that can have a significant impact to your the victim's execution time. And this is despite even if you have a cache space partitioning, you still have the bank being shared between the victim and attacker, and therefore can be affected by this type of attack. Now, the problem of the bandwidth regulation technique without knowing this bank level information is that you have to assume the worst case, and the worst case is pretty bad. And so this means existing regulation technique, like including BRU, but also RDT and MPEM, bank unaware, and therefore cannot be very effective when applying the regulation. So what we propose is basically, let's regulate at the bank level so that you can, have the same degree of isolation, but with much better efficiency, because you don't need to, limit your budget to considering worst case scenario. So we have implemented this technique in, again, the RISC-V platform, and this is the result. So what you can see here is that when you regulate the cache bank bandwidth accesses without the bank information, we can actually achieve the isolation that we desired for the real-time task, of course, but the cost is very high. So the cost is that you have to throttle the best effort task significantly to achieve this kind of isolation. However, when we regulate at the in a bank-aware manner, you can reduce the cost significantly because effectively it gives you double or quadruple bandwidth that you can use when the access to the caches are more evenly distributed.
Is it again done with boom cores?
Yes. This is boom core. All right, I think that's kind of it. And so basically, hardware interference channels on multi-core processors are a serious threat to the safety critical real-time application, and existing techniques such as space partitioning and bandwidth, even bandwidth throttling may not be sufficient. And the reason for that is that they are unaware of this physical organization of those shared resources, and therefore can be ineffective in mitigating this type of attack. So we believe better hardware is needed, and we also believe we can actually design such a hardware without massive redesign of the microarchitecture. So these required hardware support can be easily integrated into existing microarchitecture, and then that is what we are trying to do. Well, that's it. Thank you for listening, and these are the papers that we have published over the years in this topic, and these are the funding sources that we have received. All right, thank you.
We have consumed the allocated bandwidth for this talk because we had a lot of interaction, which is always great to see. But I think we have time for maybe a couple of questions if you have burning questions. He's around through the day, so you can also approach him throughout.
Thanks.
As an attacker, is it possible to detect which single bank is critical to the target process in runtime?
So actually, it doesn't matter which bank. I think so the important thing is that the distribution of the access is more important than which bank that you are accessing. So from attacker's point of view, if you target any single bank, and if you can overwhelm that, then the victims will suffer anyway, because the victim usually don't control accesses, and therefore, on average, all of those banks are kind of utilized evenly. And so if you target any one of those banks, and then you have a problem.
It doesn't matter with any single bank.
Right.
So many of these attacks, go ahead.
No, please.
Many of these attacks that you mentioned required your ability to extract the physical page address of the backing memory of what you're using.
Yes.
And I know that those sources are locking down. It's getting harder and harder to get that information. So what happens when we restrict that, when you can't get it from user space anymore? Is this still feasible? Can you still run these kinds of attacks if you aren't?
So, I mean, these information are already not publicly available most of the times, but yet people have come up with ways to reverse engineer this information, and that reverse engineering is actually, it's not very difficult.
Okay.
So, and then the problem, of this, obfuscation is that, I mean, you can kind of hide those information, but then when you discover it, it is unfixable. It is basically there, baked in hardware, and then once you determine, oh, this is how this mapping. Yes, there are people. I mean, Intel, for example, the cache mapping is very complicated because they use some weird actual, combination of these memory addresses. But the people have find a way to recover those information, even if it's quite complex. Then, and once it is discovered, then there's no solution to that problem.
So my follow on then is how could the memory subsystem of the kernel itself not help with this by migrating pages, by changing page mappings? Or if you notice that something is overwhelming the cache, maybe it's time to remap the page underneath that to try and
So
Balance out.
about that particular case, the kernel cannot do anything because the mapping is below the page address boundary, and therefore
Why can't I reassign a new physical page to that virtual one? Right, I take that physical
So
page
the
away from you. This
physical-
physical page is the problem.
so the kernel can control the virtual page to physical page mapping, right?
Yep.
But that below the page boundary, if you the kernel has no control because it is directly mapped, right?
Understood,
Yeah.
I understand, but how is migrating the page not also
No, but
mitigating?
think about if the mapping is in cache lines inside the page, even if you migrate it,
Okay, so if we're talking cache line level,
Yeah, yeah.
absolutely.
The same.
But I guess what I was getting at is that you talked earlier about partitioning via page color.
Oh.
That's right, and so, okay, like you're not gonna mess with that, and actually, I think page coloring is not a great idea in general, but I guess. Yeah, this is more talking about the DRAM channel focusing attacks that you were talking about. It doesn't do anything for the page, the cache line itself.
Yeah, so the DRAM level bank mapping is more. The kernel can do a little bit about it because usually the mapping address bits are higher than the page boundary. But the cache bank or attack, there's no way that the kernel can do anything about it.
one cute idea coming off of this, of course, you can regulate by stopping the core for a little period of time, which is, but if you are in the kernel, you could also maybe invalidate the corresponding TLB entry of that page. It's kind of like slowing down access to that page. You could do something like that if you would, but maybe it's drop in the ocean rather than being really effective.
So you spoke about how this information is usually hidden, and it's a disadvantage for like bandwidth regulators, because while an attacker can poke around or just do a full blanket covering attack and then target all the banks, you as a regulator, you need to know what is going on in this kind of different banks, either cache or DRAM, right? And I mean, since you already know that it is possible to reverse engineering the allocation, right? When you say better hardware, is it just maybe more open specifications, the solution? Like, hey, if these addresses are mapped to this bank, these other addresses, because usually this information is not available in technical references, right? If you add those information, would that be a first step into like having an easier time into defending from these attacks?
So the answer is yes and no. I mean, no in the sense that, for example, in the cache bank attack, that actually in that case, the mapping information is publicly available, right? And so we actually just look at the reference manual, and then we clearly see this bit 6 is used to determine which tag bank that it goes to. So we just use it. Okay, so then we can create the mapping. Attacker that exploit that information, and that because that bit 6 is below page boundary, of course, you can do whatever you want, right? And that is exactly what we did. And there's no fix for that. So just making it publicly available, I mean, it's not necessarily any solution to that problem. But in general, of course, if it is more available, then we can come up with a better solution. So that is a good thing always, yes.
The thing that confuses me, which is what I asked the previous question, was if I know that bit 6 puts me in this bank, why am I not partitioning so that only this application is allowed to access these cache banks?
But yes, you can do it, but it is impossible to write a program that
Doesn't use anything with big
right.
six
Yeah, for
as
example,
one
right.
value. Yeah.
Okay, and it's not possible for the operating system to.
Yeah, it is not possible, right? So operating system can't control, and application in theory can control, and that's exactly what we did, right? But I mean, in practice, if you just allocate a bunch of memory, then of course, some of those memory will be 0 and 1, and that is something that it is impossible to ask the programmer to be able to control.
So why then introduce an hardware throttling rather than an assignment?
Rather than?
An assignment, saying that these banks are for, like, you can assign processes to certain banks.
So okay, so that's the viable solution, but I mean, viable solution in the sense that the, so if you somehow be able to, physically bound a certain cache bank to a certain core, that means that you don't have access to the banks that you are not mapped, right? So you're basically losing the capacity, obviously, right? And basically it's basically private cache. At this point, it becomes a private cache, not anymore shared cache, right?
Okay.
All right, again, it's great to see a lot of enthusiasm for this level of work, which is well into your wheelhouse, sorry. So yeah, please, reach out to Ichul even after has left the campus. And again, he's gonna be around today, so please stop by. We're gonna have some talks throughout from 2 to 4. Now we bring him for lunch. Again, thanks a lot, and thanks, of course, Ichul for coming
Thank you
here.
very much.
Yep.